Oh, wow, that was cool. It's one of those few times where I'm like backstage glued to the screen. I'm like, well, that's a really good stat. I'm gonna write that down and say it later, but you already heard it, so I'm not gonna say it right now. That was awesome. I love these conversations. It's part of the reason why we're gonna be doing data center power is because of many of the numbers and stats and metrics that were shown here. All right. That was an amazing warm up, right? And now for the highlight of this morning, our featured keynote speaker. He's getting ready back there. Look, the rise of this little acronym called AI is reshaping the data center landscape. I don't think we need to go further into that one, but it's creating a demand for faster, more efficient, more scalable architecture that's simply capable of the demand of what we're seeing in today's architecture. A demand for data centers that can support upwards of 100,000 GPUs or more. Actually, at GTC this year, Jensen Huang talked about a data center that you can see from space with 1 million GPUs. Now, I don't know if Wade's going to be coming out here and talking about space data centers, but he's going to be talking about some really cool things. In fact, in his keynote, Wade, who is the chief data center engineer at NVIDIA, is going to explore how NVIDIA is tackling this challenge with innovative approaches, new technologies, and including things like digital twins for the modern AI era. But I want to get you guys a little warmed up. So I got a fun little video I want to play with you really, really quick. So check this out. Before we introduce Fade, this is really cool. Check it out.
The world is racing to build state-of-the-art, large-scale AI factories. Bringing up an AI gigafactory is an extraordinary feat of engineering, requiring tens of thousands of workers from suppliers, architects, contractors, and engineers to build, ship, and assemble nearly 5 billion components and over 200,000 miles of fiber, nearly the distance from the Earth to the Moon. The NVIDIA Omniverse blueprint for AI factory digital twins enables us to design and optimize these AI factories long before physical construction starts. Here, NVIDIA engineers use the blueprint to plan a 1 gigawatt AI factory, integrating 3D and layout data of the latest NVIDIA DGX SuperPods and advanced power and cooling systems from Vertiv and Schneider Electric, and optimized topology from NVIDIA Air, a framework for simulating network logic, layout, and protocols. This work is traditionally done in silos. The Omniverse blueprint lets our engineering teams work in parallel and collaboratively, letting us explore various configurations to maximizing TCO and power usage effectiveness. NVIDIA uses Cadence Reality Digital Twin, accelerated by CUDA and Omniverse libraries, to simulate air and liquid cooling systems. And Schneider Electric with ETAP, an application to simulate power block efficiency and reliability. Real-time simulation lets us iterate and run large-scale what-if scenarios in seconds versus hours. We use the digital twin to communicate instructions to the large body of teams and suppliers, reducing execution errors and accelerating time to bring up. And when planning for retrofits or upgrades, we can easily test and simulate cost and downtime, ensuring a future-proof AI factory.
That was so cool. I was backstage watching. That was absolutely epic. All right, well, we're gonna dive into this conversation right now. Hopefully they got your energy pumping. I am so honored and so proud to present an amazing human being and a friend, Wade Vinson. Come on, let's talk about some cool stuff. Big round of applause. All right, good luck, man.
Well, maybe it's because that video is something that I've spent 30 years on my career on. I kind of get emotional every time I see it. I'm very excited to share with you how we're bringing this vision into the future as we talk about an AI factory. I'm also really excited to share our message that came about a month ago at GTC. Jensen Huang, our CEO, he talked for 2 hours without speaker notes, without a net. I don't have 2 hours, I got 33 minutes, and I'm not gonna cover all the topics Jensen covered, but I wanna spend about 10 minutes talking through a little bit of the technology and the business side, that what it means for people in this room, what an AI factory is, what it means for people building data centers. We're gonna talk about why that trend is definitely going to continue. And then how is an AI factory different than the data centers that we all know and love and build for as many years as we have? And then finally, I'll wrap up with the tools that were given to the industry so they can be there. But I always like, when Jensen was talking, he said a few things, and I just remember another one, my heart stopped in a good way. He got up there and said, every single data center in the future is going to be power limited, and that your revenue is limited if your power is limited. I didn't know what Dave was going to say before me, but I think it's kind of the same thing. We also want to make sure that we have the most efficient compute possible. So let me translate that in that every watt that is not going to a token is money that your customers are leaving on the table. The other thing is I tried out our North Star, I'll call it a metric, the grid to token conversion efficiency. Where's Christian? Not as sexy as PUE, I admit, but maybe time will tell if the grid to token conversion efficiency, matters. And it matters because an AI factory is simply a factory. It's where the intelligence is made, and that intelligence is money. So, okay, he talked about a gigawatt scale AI factory. Let's look at one. So from our friends at Crusoe, who allowed me to, this is a drone from last Wednesday of a 1 gigawatt AI factory under construction. And right in the middle of the picture, you see these two little gray boxes. That is the substation to convert the 1.21 gigawatts of electricity that this factory needs. And so if you look at those little squares, those little 4-packs, let me zoom in a little bit. And so while a lot of people have a hard time picturing an AI factory, each one of those little squares is a 25 megawatt hall. So there's 4 of them, there's about 25 megawatts of support around it. You see cooling flanking it. What's kind of cool is you see that on the far right of the picture, what you see is in the process 10 turbines going in that can provide off-grid power in an extremely efficient manner. And so that is a gigawatt scale, but it's not that different than the smallest of the small data centers, because that 25 megawatt hall, inside of it's a bunch of hot aisle containment and power distribution. So really part of the story here is like you're already on the journey. Just because this isn't yours doesn't mean you're not already there. Now, not everybody needs to put in massive power, and not even new power. Look at manufacturing sites all over. One of my favorite pictures there in the upper left, that's the home of compact computers, where I worked for 25 years, where we used to manufacture circuit boards with reflow ovens. So there was quite a bit of power on site. Today, that is a 20 megawatt or more data center. Who would have thought that an old shopping mall in San Francisco, as you move counterclockwise, could do 3 to 5 megawatts? And one of the things about that, from a greenness perspective, in San Francisco, look at the parking lot, look at the roof surfaces that you could do photovoltaic on. So literally converting old retail spaces. In the Northeast, there's lots of mills. Matter of fact, that picture there used to have 8,500 looms in it, and it's powered by a river in Massachusetts. So talk about green power there. And then finally, old retail sites like an old appliance manufacturing site in Memphis, but I think that site's been claimed, so we won't talk about that one. But what is a real AI factory? Really, any colo that has been built in the last 15, 10, 5 years is probably got space, power, and cooling that's ready to go to actually put an AI factory in. That just happens to be Equinix down in San Jose. And we have Kid in there. We're going to talk about that in a little bit. Now, finally, the simplest thing that an AI factory is Blackwell. So Blackwell's in full production. If you look at all the logos here, all the different players that are building it across many different sizes. So people are using them at the edge. People are using them for telco, for data, and not just AI models, but for compute. I think I calculated, as I was thinking last night, that there's probably upwards of 200,000 people right now building these into AI factories around the world. Now, that's all the different flavors of it. This one of my favorite pictures again. Our GB200 Grace Blackwell rack. You know, I'll call it the smallest instance of a true AI factory, about 120 kilowatts. And look at all the vendors that are building it. And the reason I stopped there is that tells you about the scale. This isn't about a onesie, twosie that everybody's building and trying to put it everywhere. And so the state of the business is going to continue. And so one of the ways that we look at it, what an AI factory does, is today the world economy across these sectors, computing, healthcare, transportation, manufacturing, AI is in all those sectors. There's over 100 trillion. You know, again, it's the total GDP. But just think, every one of those industries is using AI right now. If we could have a 10% increase in productivity due to AI over the next 15 years, that's $100 trillion in new, 7% present value of money over 15 years. Some finance people get their calculators out checking it. That is more creation of wealth than the electrification effort. So it's affecting everything, and it's going to continue. So I want to spend a few minutes on some computer science. Jensen's a computer scientist, I'm not, but something has been happening in the last year that has really caused us to take it off. Most people understand when you look at the axis, there's a certain amount of compute on the x-axis, you generate intelligence on the y-axis, and most people know large language model. And so that used a certain amount of IT, we call it pre-training. But what's happened is the quality of these models is so much data ingestion into it, you have to do some post-training work on it. You have to send the model to school. You have to optimize it for your industry. And you want to do that without having a computer science sitting there having to teach it what a cat is, teach it what a protein is, teach it what a gas molecule in a reservoir looks like. You want to automate it. So what we're finding is that in order to post-train, it takes 30 times more compute. So as you move along the x-axis, more compute for these folks means more data centers. And then we've got, hopefully everybody's been hearing about test time training, reasoning, long thinking. And so the way we describe that is you usually ask a question at ChatGPT and an answer comes back. Well, now there are these agents. These are the AI assistants that you ask it a question, and it goes and kicks off 50 other models. And those models give an answer back. And then it compares the best answer. It's called reasoning. Well, that reasoning requires 100 times the amount of compute. So hopefully what you see is the trend line is continuing there. As we move down the x-axis, more and more data centers need to be built. Last few slides to talk about here, the only computer science. There won't be a test at the end. I do have some judges I brought with NVIDIA with me. But the business model of a factory needs to look at two things. One, on the y-axis, they want to put out the most transactions per second per watt for their data center. On the x-axis, they want each user to be happy. They want the transaction to be fast. And each one of the dots along here are different activities, different models along the AI spectrum. So Hopper is what everybody knows about. So then we came out with Blackwell and dramatic improvements, so the factory got better. Then we realized that we don't necessarily need the highest precision. So the code, the CUDA, everything working. And this is not just one model. Those dots all represent multiple points in the factory, multiple different workloads across multiple industries. It got better. Then NVL72 came out, so scaling up. So by putting more and more, so it looks like one giant GPU. So an AI factory The smallest instance might be smaller than you think, but an NVL72 is that. We continue to innovate, and we came out with a new operating system called Dynamo. And so what that does, that takes advantage of the 72 GPUs and the job scheduling and all the resources, and it's smart enough to reprioritize the resource. So while it didn't get more throughput on the y-axis, look at how much faster it answered the question, because that's what your customers want. They want to drive affinity to their factory versus someone else's because the answer comes faster. And a bit of an eye chart, but I love it because it explains how much time and effort we put into it. This is an example of a 1,000 input length string model, and each click stop along there was a different part of the potential AI factory. One of my friends last night described it. Think of this as a Honda factory. So somebody's building motorcycles, some part of it's building a race car. I don't think they do that in any one Honda factory. I'm a big fan of, I got a Civic hatchback that I love. Someone else has got an Acura RS, I think they were talking about. So this factory's got all these things, and they want to share components. And so that bright spot in the middle, that's where you want to build your factory. You want your factory to be able to have the highest throughput for some people, and you want to be able to be the fastest for other people. You want it to do inference. You want it to do reasoning. Who knows what the future of AI is going to be? We're going to talk about how people are using it to completely replace CPUs in every industry. And so there's an example of a 1,000 input model. Slightly larger model, 32,000, and models are getting bigger and bigger and bigger. But this is on a single rack, and so you can see a 40x improvement there. So in summary, this is the last computer science slide, I promise, is that your factory revenue, your end customer's revenue is going to be dictated not by the just efficiency of the design, but the efficiency of what goes in it. And so what are we doing to innovate what goes in it? So Jensen loves to show the roadmap slide, and as an engineer, I love that my boss shows the roadmap slide. I don't have to get permission and secret slides and sign the NDA. And so right now, Blackwell Ultra, we're coming out with something new every year. Rubin Ultra, and he introduced the Kyber rack. We're going to talk a little bit about that at the end. And the Kyber rack is a larger and larger scale up. So just like when we went from Hopper to Blackwell, you saw a dramatic improvement in the factory output. We're going to see the same thing as we scale up, and he even went so far as to talk about the next generation, and those will we're going to put those in many form factors. And so what does that look like? So when I talked about the smallest AI computer, think of it as a giant wafer. And so if you look at all of the components that are inside an Oberon rack, that all works together seamlessly, and that's the physical rack there, the one that everyone's building all over. And then we talked about how important scale up is. There's a Kyber rack for comparison. So when you look at the improvement that we saw when we went from Hopper into Oberon, the improvements that we're making in the models, the improvements that we're making in the silicon, you can clearly see why this trend, we really are excited about it continuing. So in the last 20 minutes here, we're going to do two things. We're going to show you what the fundamental difference between an AI factory and a data center of today is that you know and love. And then we're going to give you the tools that show you how that you can benefit from it. So really the biggest difference between an AI factory and a regular data center is probably the interconnectedness of the kit. Is that it all wants to be thinking, it wants to be sharing resources. It's definitely going to be higher power. It's going to have liquid cooling in it. But there's people in here, mechanical engineers, electrical engineers, designers going, God, that looks like the same data center I'm building. It sort of is, but you need to know what goes in it. That's a fundamental difference. So for the data center people, I hope nobody was scared when they heard AI factory, AI factory. The answer is it's what you're building today with a few differences in it that allow your customers to make so much more money out of it. And the first thing is cooling. The future of IT, 88%, in our Vera Rubin timeframe, we predict that 88% of that won't just go to liquid cooling, but it'll be cooled by a waterless dry cooler. So no compressors. And the other 12% is really just to keep humans comfortable in the data center. It's not that much left over. But if you think about that, that unit right there, that's a 400 kilowatt unit. And that unit, in the worst day of the year, only consumes 2% of the power. Annualized, it's less than 1%. So what that means is if you look at a regular data center efficiency, when you do this type of cooling, it's 25% more power you can put into tokens. So that literally, we just got a quarter of the world of data centers over again for free when we go to this technology. I mean, that's a huge improvement. Not to mention that the electric bill's cheaper as well. That's kind of nice long term. The other thing is the kit looks a little bit different. In order to get that 50x performance per watt, you think of Hopper H100, that was designed to go into an air-cooled data center. So that looks like most CPUs. But when you go to the Grace Blackwell Ultra, when you get that 50x performance per watt, your rack looks a little bit different. The picture on the far right shows water mains, the water hoses, shows the power connections. But another interesting thing that we find is I don't know how many people have been following the OCP OpenRack v3 power infrastructure. We donated our MGX architecture to it at OCP last year. There's actually 48 rectifiers, 48 individual power supplies. That gives us a lot of freedom to improve innovation. Matter of fact, we believe that over the next 2 generations, that technology will unlock another 3 to 6% more capability to go to tokens. So we're not done. The other place that spends a lot of energy is getting the data from one end to the other, and those are lasers. And lasers have glass fibers, and glass fibers are kind of finicky. A laser costs money and draw power. And so what we've done is we've chosen to innovate at the switch level to actually reduce the number of output and input lasers at the back of each switch, and we aggregate it. So if you look at, just pick a 100,000 GPU data center with this technology, you get another 3 to 5% power that you were spending on powering lasers. Now it's a lot less because we're converting right at the die level. So all these things add up in an AI factory that allows it to get the benefits of it. And then finally, we talk about how to upgrade, and everybody wants to be in a green field. Doesn't that sound cool? It's a green field. Who wants to be in a brown field? But maybe brownfield's not a bad terminology. Maybe we'll call it not even a retrofit. Let's call it reloading. I'm on year 9 of a 15-year lease. I have CPUs that are 5 to 7 years old. My estimate, I'm sure people in this room have their own estimate, I think there's 100 gigawatts of colo space that right now fits those top 2 categories. And what I'm showing you here, and the tools I'm going to show you here, is how you can convert that. And again, just making the number, if that is if I did the math right, 5,020 megawatt halls. I bet it's more than that, but I didn't want to be too crazy. If you're an investor, or you're somebody, hell, think about your own investments. What would you rather put in there? Would you rather put kit in there that you know is making money for you, or do you just want kit in there that's helping you run your business? Of course, you want both. But because now tokens is money, that's what you want to put in there. And so one of the other things that Jensen talked about, and you can go watch his talk if you want to get into it, is now with CUDA-X, it's not just accelerating machine learning AI. Every single industry has multiple CUDA libraries that are allowing CPUs to not matter. And just one example in all of these different ISVs, all these different software companies in the libraries, with Blackwell, they're seeing these speed ups 20, 30, 40, 50x. I think we're going to continue to talk about this year. So it's not just all of the scaling laws we're breaking through for an AI factory, but even the CPUs of yesterday. Why go spend money to replace old CPUs with something? And here's the cool thing. Blackwell looks the same. So as you're designing this AI factory, you're really designing a space that is better for this next generation technology. So last 12 minutes, what are the tools you need? And the answer is, you need a really good model. And so you saw it in the video here, but this is literally my team's CAD. Every nut, bolt, screw, capacitor, wire. Christian and I did this doing modular data centers 25 years ago. We modeled all of it. And that's so important because there's no way you can build at this quality, at this scale out in the field. You've got to be able to do it, and you got to be able to iterate, but you also need to do it real time. And so when you think about a digital twin, it's not just about the design aspect. Of course, everyone in here, AutoCAD, Navisworks, BIM, SolidWorks, all the different programs that people use to design. Yes, it's that. But it's more than that. It allows us real time to make decisions about the kit there. Think about how many hours you would spend when you're changing something in your factory to write a method of procedure so you don't break anything. If you've got a full up digital twin, you're literally proving it works in the digital twin before you go do it in the field. You're making improvements along the way, especially with now agentic AI, that you can do reinforcement learning. So literally, you've fully instrumented the real life model. You've got a digital twin that is, the simulation is as good as the real thing. And so you take the real data, feed it back in, more data creation. And so these are the models. So we started pretty simply. So hopefully Hopper, we went in an air-cooled data center. So this is one side of a hot aisle containment, a hack. And so, showing that's about 504 GPUs. This was designed to go in every data center in the world. So as we were building Blackwell, we wanted to make sure that was still true. And you can see the quality of our digital twin, of our model, had to improve pretty dramatically if we were trying to do something different. And so this is what you showed in the video. It's a two-sided hot aisle containment, 1,152 GPUs, about 2.5 megawatts. Now, we did have to drag some power feeders over from our neighbors, but that's not uncommon in colo. So when we quadrupled the density, we had to borrow some power. We also brought warm water in, and when we brought warm water in, we just put that dry cooler out in the parking lot or out on the roof. You could reuse the water that you've got, but to take advantage of the energy efficiency. But that's sort of more of an enterprise model. I know, 2.5 megawatts, right? Every enterprise can afford one of these. They can put it on premise, they can put it into their colo, but what about people who are scaling? So as we scale, we started to think about what is the ideal size? And, I think we figured out, because we had a digital twin and we modeled it and we iterated 35,000 permutations, we think about 5 megawatts is the right size. And that's 5 megawatts in a colo, that's 5 megawatts at a university, that's 5 megawatts in Abilene or Memphis or wherever it's going to go, is that we think that's a good size. And here's the cool thing. You see the power in the racks. So we've got this collection of GPUs, four racks, 4 racks, 4 racks. As the power goes up today from Oberon, and we put in the next generation chip. Sorry, I don't have any better numbers about roadmap power. You come talk to me in private, we'll talk about that. But we can literally, with a 5 megawatt hack, 2 generations from now. So what Blackwell Ultra, then Rubin, that if that stays under 207 kilowatts a rack, I didn't change anything. Now, if I only designed the perimeter for 2.5 megawatts, the power feeders, the cooling, that wasn't enough. But if we design it for 5 megawatts, the kit you're putting in today, your customers will be future-proof for 2 generations coming out. That's pretty cool, but it gets better. What if some future one, because we showed you, Rubin Ultra, Feynman, what if that power goes up? Well, why not take the power from 2 racks and run it into 1? If I can do that, and yes, we could build more dense kit, but did your data center really change? When you look at all of the acreage around it, that is the UPS, that's the transformers, that's the heat rejection, that's the storage, that's the L3 switch, that's the load balancers, that's the people space, all of that was that Jensen comment he said originally. Every data center is power limited. You got a molecule on site, you got a golf ball of uranium at some point, you got a power feed. The perimeter inward is kind of fixed. And so we want to make sure, as people are deploying this today, that 5 megawatt that is future-proof. And not getting in trouble, because Jensen showed it on stage, a future Kyber. So I went from a hot aisle containment that had 24 racks, 4 in the front, 4 in the back, times 3. As power went up, I cut the racks in half. As power goes up again, I go from 8 racks to 1 high power rack. So what you see pictured here is some theoretical future that 3 high power racks, there are power sidecars that actually shim in between the data center power and the Kyber rack. And if you don't believe me, we had this really beautiful model at GTC. Oh, and there was a rack there too. So you got to see all the pieces of it, that how it actually works together, and so how far along we're on the switch architecture, how far we are on getting the power and cooling space into it. I'm standing in front of the power rack, so it's hard to see. But the net of all this is we have digital twins of it, which means you have digital twins of it. That means that you can sit down with your architects and engineers and your customers, and you can look at where your power is, and you can look at what your cooling is based on your footprint, and you don't want to use any water. We're trying to do these things to take advantage of the limited resources we got to get. Our digital demand is crazy, so we're trying to make sure that we're taking the most advantage of it. And if you think that, okay, Wade, I've seen you draw crazy cartoons over your career, and when you build it, okay, did it really fit? Well, the digital twin is worthless if you didn't build a real one. So we, working with Equinix, took a real-life data center, and we said, how do we take a real-life data center that effectively could have been built 15 years ago, and can we drop Blackwell in? Well, you'll notice here, the kit at the far left is a little bit of storage, a couple management racks. The kit at the right is the L1 and L2 switching, but then you've got the 4 Blackwell racks in the middle. And when you look at that and compare it to the digital twin, you said, man, wait, it almost looks like you're cheated. The digital twin looked busier. It looked harder to do in the digital twin in real life. I don't know if you ever do CAD, it's hard to model a hose and a power cord and network cabling. And so in real life, you can easily see that as the topology doubles over time, that I can get twice the number of yellow cables per rack, very easily. I can take the power from the adjacent rack and bring it in. So that's a cold aisle view. And why it looks familiar is there was a digital twin. So we were literally building in real time. And so we would get to the site and we would start dressing the cables, and somebody's like, it doesn't fit. And I'm like, well, it's like, you got a digital twin, how can it not fit? And we're like, oh, the as-built didn't match what was really built. How many, I'm sure everybody's been there once. And so we had to go move it. And so along the journey, we got to improve the model and improve it in real time. And so that's literally where it comes from. When we go to the hot aisle side, And our industrial design department, you know, they've got all the 2 miles of copper cabling per rack all lit up. But you can see in the middle racks that the other side of the rack, you see power on one side, the original OCP rack had the capability to bring power in from the second side. So as power goes up over time, I could take 2 of these racks out, see the water, see the power, and I could attach it together. That's pretty cool. And we proved that we can do it in a data center that was designed as air-cooled cages at 5 kilowatts a rack. So I submit if we did it there, and we've got a digital twin, that we can do it anywhere. One quick comment about the water. You want to make sure that water, you understand the energy use, you understand leak detection, and so we made sure that we had plenty of valving, and we've got a control reference design, and so this was just an implementation that the data center was already designed. So we want to make prettier water. We're going to make prettier water. So when we upgrade this, we'll give tours to it. But I don't know, as a mechanical thermal engineer, that we made it work, that's the prettiest thing of all. And then finally, this is literally the cage. So people think sometimes I'm maybe telling a story to exaggerate, but you had this room that was probably, here, that had 2.5 megawatts of air-cooled kit. Now, it's just got one SuperPod in it. Now, what is true is you see that row power panel at the end of the cage that is 250 amps. There's actually 23 more you don't see next to it that we had to scab in. But that's easy to do. We drug the power over to it. So hopefully you got to hear what an AI factory is, why it's going to continue, why the business matters, why it matters to the planet, how it's not that different than we know today. So what's the call to action? And that is, don't wait. A watt that you've got in hand from an old manufacturing site or a colo, don't wait for an interconnection study. We're showing you these tools with the digital twin that allows you to get to token creation. Every watt matters. 8766 hours a year. But what I really think is scaring my friends at Digital Realty here, when we look at this 16 megawatt data hall, and I think of it as an AI factory, I stare at that and I said, I think 8,700 hours a year, I had to be able to get 28 megawatts out of that. And they're like, sure, wait, just cut me a check and we'll buy new equipment from Verta, we'll buy new equipment from Schneider. And so we're thinking about that, because as Jensen used to say, it wasn't the more GPUs you buy, the more you buy, the more you save. Now it's the more you make. And then finally for Bill, got to change his rules, Bill. And you come up and see what I said. It's not just power and bravery, but you need really great models as well. And we're here to help you do that. And thank you for your time.